Hello everyone. In this video we are going to talk about some basics of statistics. So as you know, statistics is the science of collecting information about populations using what we call samples and then trying to analyze them, extract higher level meanings out of them and try to generalize those meanings to the larger population. So, as I said, in this video, we're going to talk about some basics, mostly what we call descriptive statistics measures that you can define for a sample. And these measures, you can categorize them into four main groups: the frequency group, central tendency, the dispersion measures, and position. And here I have color-coded these four groups with purple, green, blue, and red. And each measure here from 2 to 12, except for 10, which is a method, not a measure, for determining outliers. Any item from 2 to 12, again, except for 10, which is 10 measures, they have the same color as their category. So if an item is green, that means it's a central tendency item. If it's red, it's a position measure, and so on and so forth. So let's talk about these 10 items, and I explain the meaning of them, how you calculate them, and their application. So I jump around the list first, and I first go to histogram in the first place. So histogram is what? If you have a bunch of data that you collected from some population, which is what we call a sample, and now you want to show the frequency of each range of data, that plot is called the histogram. So here on the x-axis or horizontal axis, you have the data in general, in this case like a grade of a class, and then on the y-data, you're going to show how many of that data or that range of data you will have, so you call it the frequency. And this is what we call a histogram. So histogram is like the distribution of the data, right? How many of the data you have in each range. By the way, as I said, mostly you do not really show each individual data on this axis. Instead, you put them in specific ranges. And so instead of me showing you how many grades of, let's say, 8 I have in this class, or how many grades of, let's say, 86 or let's say 97 or so on and so forth, because I might not have too many exactly 97 grades or exactly 8, what I do, instead of having like 100 or 80 or 90 small bars, spikes, again, I consider a range. So I say, well, instead of me showing you 0, 1, 2, I put here all of the data from 0 to 10 in one we call bin, and then I count how many data will fall into that bin. The next bin is 10 to 20, the next bin is 20 to 30, 30 to 40, and so on. So I divide my whole range of data into a number of bins and count how many data of the sample falls within each bin, inside each bin, and then call it what? The frequency for that bin, and I get this bar plot, which we call a histogram. So this gives me a rough presentation of the sample, and maybe I can generalize it to the population. So for example, if this is a sample class that I have, maybe you can say, well, the grades distributed in such class might look like that, but it's not really easy to generalize from a sample to the whole population. And the reason we work with samples is collecting data from the entire population is typically a very hard task and sometimes impossible, right? Let's say here, for example, I want to look at the frequency or the number of grades in a specific class, let's say a CAD class, right? Computer-aided design. Okay, how many of these data should I collect? There are lots of CAD classes all over, let's say, the United States. and there are so many students, so many grades. How can I get every single data in those classes and then get this big histogram? It's not possible. So maybe if I want to have a rough estimate of distribution of CAD grades in the United States, I only go and collect from each university or a few universities a specific number of data, maybe one class out of each university or one class out of every 5 universities I can find, so that I can manage collecting the data and handling the data. So now whether that sample, the results of that sample, the measures of the sample can be generalized to the population or not, that's a separate story, and we'll talk about it later. But this is showing me what, for example? If I look at the center of each bin here and try to connect them together, right? It shows me this kind of rough graph. So what does it mean? It means that, first of all, if I look at my data, it has 3 peaks. One peak here, one peak there, one peak there. Now, one of the measures that you have in statistics is called mode. Mode means the data point or the center of a bin where the maximum frequency is happening. So if I want to talk about the mode here in this histogram, mode means the maximum frequency, which is here, this center peak. So if I want to talk about mode, your mode should be somewhere in this range, between 40 to 60. That range of data is where the maximum frequency happening. So this is called mode. Now, if your distribution of the data, the histogram, has one dominant peak and nothing else, so it looks something like this, right? You see, if you look at this distribution, there is only one peak. If you have one single peak in your data, then we call it what? We say the distribution of the data is unimodal, means one single mode. But not always is like that. Sometimes you have 2 or 3 or more of these modes. So if you have 2 modes, you say my distribution is what? It's bimodal. If there is more than 2 modes, we say what? You say it is multimodal. And again, as I said, if there is one mode, you say the distribution is unimodal. So this kind of distribution is unimodal. This one that I have with 3 peaks is multimodal. And a bimodal, the histogram of that would look like this. So there are 2 dominant peaks. Many times in my classes, the experience shows that the distribution of the grades is bimodal. There is a peak of low grades and there is a peak of high grades. Okay, so I just want you to know the meaning of mode and modal and multimodal and so on. By the way, if I ask you which one is mode here, really, that's this one. So mode is the data with the maximum frequency. Not every peak we really should call a mode. So the reason we call it bimodal, it's really an appropriate name for saying multi-peaks. So mode, the way we statistically define it, is only the maximum, the biggest peak, the largest peak. That is mode. This is not a real mode. This is like a mini mode, a local mode. This is like the global mode. So when we talk about this mode here, that is the only global mode, none of these small local ones. But when we describe the distribution, if you ever hear the word multimodal, it doesn't mean it has 3 peaks of the same size. Some of them could be smaller than the others. So that's the mode. The other definition that I can talk about right off the bat here is range, and I mentioned it already. Range means the maximum data that you have minus the minimum data that you have. Okay, so here let's say the minimum data of me is 0, the maximum is 100, right? So this distance between the maximum and the minimum, this is the min data, this is the max data. This distance here is what we call range. Okay, range is equal to max data minus min data. Okay, and it's a measure of course, dispersion of the data. It shows how well the data is distributed over what range. Okay, so this is about 3 of these important things: histogram, range, and mode. What else do we have? We have average and median. Average is what? Average is like the center of gravity of the data, center of mass of the data. While median means the center point of the data. Well, what's the difference? The difference is this. If you have, let's say here, a total of 60 data points, right? So sum of all these frequencies, when you add them, is 60 or 80 or whatever. If you sort your data from the smallest to the largest, so you have to sort your data from smallest to largest, then the middle data point is what we call the median. So what do I mean by that? Let me show you with some numerical values. So let's say my vector x, which is a bunch of numbers I sampled, is equal to 1, 3, 4, 2, 8, 9, 3, 5, and let's say one more, 7. So these are some numbers I have collected. If I tell you, okay, which data is the mode, you look which one has the highest frequency here. And you see it's 3 that has repeated 2 times, nothing else is 2 times. So 3 is your what? Is your mode, the data with the maximum frequency. But what is median? For median, you need to look how many data points you have. Here, you have a total of 9 data points, 9 entries. Correct? So the first thing you do, you sort your vector. And if you sort it, let's say from smallest to the largest, you will get 1, 2, 3, 3, 4, 5, 7, 8, 9. Right? Now you look at the middle point. If you have 9 data points, data number 5 is the middle point because you have 4 entries on its left side and 4 entries on the right side. So this is the middle point in assorted data. This is what we call the median. So the median here is what? 4, the middle point. And average is different. When you talk about average of vector x, which by the way you can show with the bar above x, average of x is what? You add all the data points together from 1 to n. In this case, your data is 9 points, so sum of all of these numbers and divide it by the number of data points. So for that, I need to add all of these numbers together and then divide by the number of data points. That's like the center of gravity of the data. What do I mean by that? I'll show you. So first, let's calculate this number. So here you have a 10, 13, 20, 33, and 42. So it's going to be 42 divided by 9, which is 6 over 9 or 2/3, this much. 4.67 is the average. Now you see your median is 4, your average is 4.67, and your mode is 3. Okay, so these are different numbers. Now, you can see them here also on this histogram, that if you have this histogram of the data, the mode is the peak location, Median is if you have all of the numbers sorted, the middle point of the data, and then average is like the center of gravity. So if you consider the data to be like this is like a seesaw. So if you have all this data here, and if you have all the data on the right side of it, you can easily what? Balance the two. What does it mean? It means sum of the distances between the data on the left side to the average is equal to sum of the distances from the right side to the average, correct? So summation of, or you can say summation of xi minus x bar as I goes from 1 to n, when n is the number of data points, this is equal to what? 0. So some portion of this data are on the left side of it, some portion on the right. But when I add them together, since they are equal, if you consider some of them positive, some of them negative, then the total will be what? 0. So this is another way to describe the average. And you can see that through this definition too, right? This is your n. This 9 here is your n. And if I replace it here, what do you get? Look at this and cross multiply it. You will get summation of the data is equal to n times x bar. Correct? And so if you bring this term to the left-hand side, because the right-hand side you can write it as summation of x bar I from 1 to n, correct? X bar is constant, so when you add it n times you get n x bar. If you bring now this term to the left-hand side, since they both have the same summation, you can subtract and you will get this important thing. Right? So this is another way to describe the average. That sum of the distances of data points to the average, when you add it over all data, that is equal to 0, so you can call it like a center of mass of the data. Now, this term here, by the way, the difference between each data point to the average is what we call deviation. And we'll use it later when we calculate the standard deviation. So deviation is the distance between each data point to x bar. So if you subtract these data points, all of them from 4.67, that gives you the deviation for each data point. Okay? So now, why is it that the median and mode are different, and which one is used in practice when, how? So sometimes, as you can see in this figure on the right, the median, mode, and the mean could all, or the average could be all on the top of each other. And this is only happening when your data is perfectly symmetric about the middle line. If your data is perfectly symmetric, which we, by the way, this kind of distribution is what we call a normal or Gaussian distribution. Do a little bit of cleaning. Okay, so it's called normal or Gaussian, or might call it bell-shaped distribution of the data. This happens in the nature when there are so many factors contributing to something, and so the total effect of all these factors makes the distribution of that final variable to be what? To be Gaussian. That's what we call in statistics central limit theorem, and I'm going to talk about it later. That's a separate video. But this normal distribution happens again in nature when there are so many contributing factors to your sampled variable. But many times in nature, the distributions are not perfectly symmetric. They are what we call skewed to the left, skewed to the right. There are several peaks, multimodal, and so on. So that's where your median, mode, and mean or average could be quite different. Now, which one is useful? Which one do we use in the literature a lot, and why? So The average is a very good representation of the whole population or the whole sample when your population is symmetric like this. When your population is quite symmetric, the average shows what is the typical, right, or what is the data with the maximum frequency happening, what is the average of the data, and so on. Let's say, for example, if I have the annual income of a household in the United States, if I look at the distribution, and this distribution is quite normal like this, let me show it this way. Okay, and let's say this average is, for example, based on the United States Bureau, is like $54,000. Okay, so that tells me if I go and ask an average person, how much is your annual household income? I have a higher chance of seeing people with this much income or close to this much than people who have far less than this much income, or what? Far more than this much income. So if I go and ask for $5,000 versus $500,000, I see a lot less 500 and a lot less 5,000, but I see more close to 54 or something, right? So it shows me the center of gravity, the representative of the society, right? I see the data with the highest chance of seeing, the highest probability, or the maximum frequency. But when the data is skewed, that's a separate story. Why? Because the data that are very large or very small, which later we call them what? We call them outliers. They can easily change your average in a very significant way. They can completely change your average. Why? Because they are here added to every other data. So their weight, their effect is really significant, right? Let me show you with a number here. So what we can do here is, remember here the average was 4.67 with the data that I had. Now I go ahead and add one more data point to this data set that I have, and I make it quite large, okay? So quite different than the rest of the data. Let's see what we get. So here I say my data is, it is 1, 2, 3, 4, 5, 7, 8, 9, and then I add maybe a 30. Okay, so here what's going to happen is my new x bar is going to be what? It's going to be sum of all these numbers divided by, now I have 10 numbers. So whatever I had earlier, which is sum of all of this, I have to now add a 30 to it, so it's going to be 72. And this 9 becomes 10. So now look at your average. It's going to be 7.2. So just by adding one significantly different number than the rest, which we call an outlier, now my average has changed significantly from 467 is now 72. It has changed. If you look at the percent wise, it is about a little bit less than 2 times. So it is added like 70-80% increase in the average, correct? But if you look at the median, what was the median last time? So the median of x, if you remember last time we had 9 data points, it was the middle point, so it was 4. Now what? Now how much is median? So median here again is the middle point when you arrange the data from smallest to largest or largest to smallest. Now here you have 10 data points. When you have an even number of data, there is no middle point. When the number of data point is odd, you always have the middle point. When it's an even, you have 2 middle points. You have 4 and 5. Both of these are middle points because now you have 4 to this side 4 data here and 4 to this side of 5. So both of these are middle points, and so the median is going to be the average of the two. Now look at the change here. It gone from 4 to 4.5, but the average gone from 4.67 to 7.2. So this is a what? This is 1/8. This is like 12.5% increase with the outlier. While here with the average, if I calculate it, so this is going to be 7.2 minus 4.67 divided by 4.67. It is 54% increase. So you see, adding a single outlier can affect the average a lot more than it can affect the median. That's why when the data is not symmetric, where there are outliers, we typically use the median instead of what? The average. And that's what you see in many of the websites when they want to talk about, let's say, the house price. Let's say when you go to Zillow, you are looking at the price of the houses around you that are sold. It doesn't give you the average house price list, it gives you the median. Or if you look at the household income, annual household income in a country, now they are showing median numbers, not average. Because the very low incomes and the very super high rich will completely change the location of the center of gravity. But they cannot change the median so much, because all the median is affected by is the number of data points, not the size of the data points. Okay, so median is way more robust to outliers than average, and it's quite a better measure that we use in statistics or machine learning and so on. The hard thing about median is calculation of that is a nonlinear operation. Average is very linear, okay, just add the numbers divided by n. Median is not. You have to add the number of data points, find, sort, and then either look at the median, the middle point, or the average of the two middle points. So it's a nonlinear operation. That's why applying it for machine learning or other purposes is a little bit harder than the average, because linear operators have a lot of useful properties that the nonlinear operators don't. Okay, so just keep that in mind. And as I mentioned, let me just write it down for you. So if n, the number of data points, is odd, right? It's like 2k plus 1. The number of data points is an odd number, then the median is going to be what? Is going to be the middle point, which is what? K plus 1, correct? So this is going to be data k plus 1 if it is sorted. Data k plus 1 in sorted sample. If, on the other hand, your data has an even number of entries, then the median is going to be equal to what? To the average of the two middle points. And the middle points are k, correct? And what? K plus 1, correct? Which both have a k minus 1 data points on their left and right. So it is going to be data number k plus data number k plus 1, the average of the two in the sorted sample. Okay, so this is how you calculate the median. Okay, now before I do anything else, let me show you the example here. So here I wrote a MATLAB code that generates 95 integers, random integers, and they are all between 0 to 100. or 1 to 100. So let's say these are the grades in my class, and I have 95 of the students. So here I'm just getting some random data by MATLAB, but in real life, these are coming from actual physical data. So here is your sample, and you can draw the histogram of the sample by just passing the number of bins to it, or the command histogram in MATLAB, you can pass the ranges of the bins, so the min and the max of each bin, if you don't want the bins to all be the same size. And this by itself will give you the histogram, like this. By the way, each time I run this code again, it gives me a different histogram. So you see this one is different than this one. Why? Because my data are random. Okay, so this is kind of more uniform than the last one. And uniform means, if you look at the distribution, by the way, let me tell you this terminology. The distribution, the frequency of the data versus the data is kind of constant. So if you have such a thing, this is called a uniform distribution. We'll talk a lot more about distributions in the future, but I just want you to know the difference between a uniform distribution and a Gaussian or normal distribution for now. Okay, so here I calculated those numbers. Now there are 95 of them. Am I going to show, if I want to tell you about the grades in my class, am I going to show you all of these, all of this data one by one? No. And even if I show it to you, it doesn't mean anything, because it's just a bunch of numbers. It's always good to show a single picture like this that tells you the distribution of my grades. A picture here can be better than 1,000 words or 1,000 data. So that's what you see. Instead of me showing you all of this, now I show you what? I show you the range of the data, which the command range does, the average, the median, and the mode. So look here. It says the average is 46.6, the median is 44, and the mode is 19 in this set of data. Minimum is 1, maximum is 100, range is the difference between them, which is what? 99. So we have all of these commands, min, max, range, mean, median, and mode, and we have the command histogram in MATLAB that can help you with your statistics. Good. Again, you can provide the number of bins or the range for the bins, the min and max of each bin. So these are some of the initial measures that we have covered together. Now it is time to move on to the next level. So before me going to talk about the standard deviation and variance, there are a couple of things that are related to median, and those are percentile and interquartile range. Let me talk about them first, and then we go to standard deviation and variance. So if you remember, I told you when you want to calculate the median, you have to sort your data from smallest to largest, or largest to smallest. Now, what you can do is you can say, well, my smallest data is the 0 percentile of the data. And my largest number is the 100 percentile of the data. So if you say the whole range of the data is equal to going from 0% to 100%, that's equivalent to the whole range, then where is the 50% of the data? Well, that is going to be your median, right? So median is where you have the 50 percentile or 50% of the data. That's the median, correct? So median is 50%, min is 0%, and max is 100 percentile of the data. But you can define other percentages as well. Like if I say, what is the 25th percentile of the data? You say, well, if mean here, this first one is 0, the median is 50%, then I can say that the data between the mean and the median is the 25 percentile, right? So I can say this data here, which is between 1 and 4, this is what? This is my 25th percentile. Right, so this is 0th percentile, this is 50th percentile, this is 100th percentile. And I can say here, this data is what? This is the 75th percentile. Right, so I can define different percentiles for different locations. Now, what if you define a percentile that does not exist? Let's say here, I say, for example, what is the 30th percentile of this data? So I say 30th percentile of this data is what? So here is 25, this is 50. So this data is clearly not, that's the average of the two. So this data here, if I want it, that's 25 plus 50 divided by 2. So that is 37.5 percentile. So that's not the 30th percentile and not this one. It's somewhere between these two. Correct? How would you find it? Because there is no such data here that I can assign it to the 30th percentile. You have to do an interpolation here. You have to say if 25 is equal to 3 and then 37.5 is also in this case 3, then 30, which is somewhere between these two numbers, is what? Is a linear interpolation between these two numbers, which in this case it also happens to be 3 because the two sides of it are 3. But let's say if instead of 30th, I say what is about, let me use a different one. How about 60th percentile? 60th. Right, now what? So for that case, you need to find the data that the 60 is between those two. So this is 75, this is 50, this is between them, which is 62.5. So the 60th percentile is somewhere between 5 and 7. But how do I find it? As I said, with linear interpolation. How do you do it? You say, well, it is equal to 60 minus 50 divided by the whole range, which is 62.5 minus 50. Correct? This is the proportion of the percentile between the 60th to 50 and then the 60th to 62.5, because 60th is somewhere here, right? It's between 50 and 62.5. So we do a linear interpolation that times the whole range of data, which is basically 5 minus 4, correct? So this 12.5 percentile corresponds to 1 unit of change in the data. What about 10% of it? Okay, you find that, and then you add it to the data that was at 50th, which is 4. So this is a linear interpolation. So it is going to be 10 divided by 12.5 plus 4, which is going to be 4/5, correct? If you divide, yes, 0.8. Good. So it's going to be 4.8. So when the percentile does not exist, what you need to do is to do interpolation between the two closest data, the two data that this required percentile is between them. You do a linear interpolation and find it. And that's exactly what the command percentile in MATLAB does. So if you use the command percentile in MATLAB, which is PRCTILE, you pass to it your vector and you pass to it the number, which is between 0 to 100. So this gives you 25 percentile, this gives you 75 percentile. If you want a 30, you can plug in 30, okay? So this is the command to get it. And this is the mechanism that it does it, based on the sorted data and then corresponding data from smallest to largest to going from 0% to 100%, okay? That's called the percentile, right? Now, median is definitely the 50th percentile. Now, there is a term here that is called interquartile range. What is interquartile range? That's the distance between 75 percentile and 25 percentile. Okay, so this distance here. And move this down. It's the distance between 25 and 75 percentile. This distance is called the interquartile range. Okay, and in this case it's 7, which is the 75 percentile, minus 3, which is the 25 percentile. So it is going to be 7 minus 3, and it is 4. 4 units correspond to the middle 50% of the data. So what's the meaning of this? It's the middle 50% of the data, or the 50 percentile of the data. That's interquartile range. In MATLAB, there is the command IQR that you can use to give you that. Okay, there is this command IQR, which gives you directly, or you can get the percentile 75 and the percentile 25 and simply subtract it. That's all it is, IQR, okay? So this is the interquartile range. Now you might say, okay, fine, I know that. Now what's the point? I know that median and average can show me the center of the data, a representative for the whole data. Median is when the data has skewness, or it's skewed to the left and right, it's not symmetric. Average or mean is when the data is relatively symmetric. Mode just shows me where the maximum frequency of the data is. Histogram, the meaning is clear. What about percentile or this interquartile range? What's the use of that? And the use of that is this item number 10. It's a method in statistics called box plot method, which is used to determine the outliers in a set of data. The data that are too large or too small that they are not matching the rest of the data. For that, I need to know the percentile and interquartile range to determine the box plot, and the data inside the box plot are considered inliers. Anything outside that box or that range that this method gives me is called an outlier, okay? So that's where we use it, and I'm going to explain it right now. So the box plot method says, if a data is inside the range of the 25th percentile minus 1.5 times the interquartile range to the 75th percentile plus 1.5 times the interquartile range. As long as your data xi belongs to this range, this is what we call the inlier, or the data that should belong to the set normally. If it's outside that range, that's what we call an outlier. Okay? So let me just put it somewhere for you, like here, correct? So this is the definition of an inlier. And anything outside this range is what? An outlier, okay? So, for example, here, if I go back to this array that I used, what I need is to calculate the IQR, which is 4 here. The 25th percentile is 3, the 75th percentile is 7. So the range for me in this case is going to be what? In this case, the box that includes the inliers is going to be the 25th percentile, which is 3, minus 1.5 times the interquartile range of 4, to 75 percentile, which is 7, plus 1.5 times the interquartile range. So this range is going to be what? It is going to be -3 to 13. So if any data is between -3 to 13, that is an inlier. Outside that, which means less than -3 or more than 13, that's an outlier. Now, in this case, none of this data is outside the range, so I can call all of them what? An inlier, correct? But if I had some more data, right? Or let's say if instead of this 9, I had a different data, let's say instead of this 9, my data was what? It was like 15. Then 15 does not belong to this range. So I would say what? I would say 15 is the outlier in this data. And what do we do to outliers? One of the typical things we do to outliers, we try to not include them in our analysis. Like when we want to calculate the average, we calculate the average of the inliers only and neglect the outliers, or the median, or the median is not that sensitive, but the average is. So if you want to have an average or maybe a standard deviation, which we're going to talk about next, these two measures, which we see a lot in statistical analysis, these are typically calculated first by finding the outliers, not including them or throwing them out of the data, just neglecting them, discarding them, and then go ahead and calculate the standard deviation or average. Okay, so that's how this box plot method determines a range based on the 25, 75 percentile and the IQR, and any data outside the range called outliers, so we can neglect them for several calculations in statistics. So here is the MATLAB code that I have for the box plot method. You can see I got the 20 and the 25 and the 75 percentile numbers using PRCTIL command, and then I used the IQR command, added and subtracted 1.5 times that to these two numbers and get the min and the max of the box. And now what I do is I will look at the values in my vector, in my sample, that are either bigger than the max or they are less than the min, and call them outliers. If this outlier is not empty, so there are some entries in X that are outside the range, then I'll show them. Otherwise, I say that if it was empty, I said there was no outlier. So in the case of this example, if I run this code, right, you see there was no outlier in this case, because the range that outside of which can be called outlier for me is -64 and 158, and all of my numbers, random numbers, are between 1 to 100. So there could not have been any outliers. But if I used the X vector that I mentioned earlier, right, so if I go ahead and change my X and say X is equal to that 1, 2, 3, 3, 4, 5, 7, 8, and instead of 9 I use 30, correct? So I change my X, and now if I come and run this again, Now you'll see that my minimum of the box is -4 and the maximum of the box is 14. So any number bigger than 14, less than -4 is an outlier. So if I run this, it should tell me that, hey, that number 30 is an outlier. Look, you see the outliers in the box is that number 30, okay? So this is how you do the box plot in MATLAB using a simple comparison or a logical array, basically. So let's go now to the standard deviation and the variance. So if you remember, I mentioned that the difference between each entry in your sample and the average of the sample is what we call a deviation. Right? That was the definition of deviation for each entry. Now, the question is, if I add all these deviations together for all of the data, you remember that sum of it is going to be what? Equal to 0. Correct? That was another way that we defined the average. So the sum of these deviations is not going to give me anything. So it doesn't matter how much these deviations are, if they are really large or really small, if the data are far from the average or they are very close to the average, it does not matter if I simply add them together. In other words, if I want to distinguish between these different distributions that you see here with different colors, well, in the blue, the data are kind of clustered very close to the center, right? So the deviations are small, while in the green one, the data are well spread and the deviations could be very large on average, correct? The red one is somewhere in the middle. Just adding these deviations by just looking at their signs, so some of them are positive, some of them are negative, right? If some number is on the left of the center, here is the deviation for it is going to be negative. If some number here is on the right side, the deviation is positive. So sum of those positive, negative is 0. That's why you don't get any meaningful thing out of it. But if instead you square it, so you square each one of the deviations and add them together, now you're adding a bunch of positive numbers together. Right? And so some of it is not going to be 0. And of course, the more spread, the larger the spread of the data you have, these deviations are going to be larger, the square is going to be larger, and adding them together give you a bigger number. Okay, that's why when you add all of these deviations together, the square of them, that is a measure of the spread of the data, how much the data is spread from the center. And that's why when you use that and divide it by the number of data points minus 1, you call that entity the variance. So the variance of a set of data is equal to summation of the deviations squared divided by n minus 1, and the standard deviation is the square root of the variance. So if this entity is variance, that you might show by s squared or sigma squared, then the standard deviation s is what? Is the square root of the variance. So some people might use variance, some people might use the square root of that, the standard deviation, as a measure of what? The spread of the data. Okay, so the definition of standard deviation and variance is quite clear. Why do you take a square root? Because here you square these deviations. If you take a square root of that, it is kind of more, or it's closer to the actual deviation terms themselves instead of the square of them, right? So this is kind of like an average of the deviations. That's why we call it standard deviations. But again, since you have a squared, if you take the square root, it is more in terms of magnitude closer to the deviations themselves than the variances. That's why you take a square root. Now, the one question that might make you interested is why n minus 1? When we calculated the average, we divided some of the numbers divided by the total number of entries, right? So we used n, not n minus 1. Why is it that in the variance of a sample or the standard deviation of a sample, we use what? We use n minus 1. What is it? So the reason for it is something called a bias. Bias. We are trying to avoid bias. Now, what does that even mean? So this is a little bit beyond the level of this lecture, but what it is if you remember, I told you that you have a population, correct? And this population or community has lots of data. If you really want to measure the standard deviation of the population, whatever variable that you are measuring in that population, if you are trying to calculate the standard deviation of variable x, okay, and call the standard deviation or STD of this x, if you call it sigma, right, you can never actually measure the sigma, because for that you need to have each and every number in that variable x, which means that variable, whatever it is, you have to go and measure it from each single member in the population. Let's say, for example, that's what? That's the standard deviation of the male height in the United States. Well, could you go and measure the height of every single male person in this country, put them on a huge data sheet, and then calculate the standard deviation? Well, that's a very hard job. So what you do instead, as I said in statistics, you go and sample this. You just go and measure the height of some people, not all. So here you get a sample instead, which has a lot less number than this x. So you have something like this xs, which is like a sample of x, and calculate the standard deviation of that, and you call it s, just like what we did. Now, the matter of fact is this. If I calculate this s by taking the square root of variance, which is sum of the deviations, correct? And if I divide it by n, not n minus 1, just by n, if I do it this way, then you can show mathematically that the number that you get for the standard deviation of the sample is going to be different than the number that you get for the standard deviation of the population. So your goal is ultimately that this s can what? Can represent sigma, right? That s could be a good approximation to sigma. That's what you try to do. Try to generalize the measures of a sample back to the population. But the matter of fact is, mathematically you can show, again, it's beyond the scope of this lecture, but mathematically you can show, if I use n here, not n minus 1, then whatever I get for s here is going to be actually a little bit less than sigma. So s is going to be a little bit less than sigma, even if I increase my sample size. So even if I get bigger samples and I make the n to get larger and larger, still I can show that s is always an underestimate of the actual sigma. Okay, assuming that the population has a normal distribution on that variable x. So the distribution of x, frequency of that variable x, if it's a normal distribution, you can show that if you use a formula with n in the denominator instead of n minus 1, s is always underestimating sigma. And you can show that if instead of n, you make it n minus 1. Then, as n gets bigger and bigger, as your sample gets larger and larger, s is actually going to converge to sigma. So when you make your sample larger, your estimate of the standard deviation of the sample will be a very good approximation to the standard deviation of the population. So here, that is always easier. We say this estimate has a what? It has a bias, or it's a biased estimate of sigma. It's turning it to always show a smaller number for sigma. It has a bias, right? It doesn't show the actual entity, while here it does. You just need a big enough sample. Okay, so to avoid this bias, mathematically you can show all you need is to change that n to what? N minus 1 to make your estimate of S be more accurate and generalize it to the population. So that's why there is n minus 1. So hopefully that's clear. In MATLAB, the command std can do the job for you. So let me show you. That's this guy here. And the command var is going to give you variance, right? So here, all I need is to provide those commands and vector x, and it will give me a variance here, and it will give me the square root of that variance, which is the standard deviation. So if you look at this data, you clearly see that the blue distribution, which is very narrow cluster, everything is close to the center, has a smaller standard deviation, or S. Red has a little bit bigger, and green has a lot bigger, right? So the bigger the standard deviation, the wider the distribution is going to be. That's why standard deviation is a measure of what? Dispersion of the data, as well as the range. But clearly the average, median, and mode that are talking about the center and how the center of the data is, where is it located, and so on. They are central tendency. The percentile and the interquartile range are going to show you about position of the data, right? Or position, percentage position within the data. In that aspect, median can be both. Median can be both a central tendency and a position. And the last two metrics that we need to talk about are called skewness and kurtosis. So these are the last two things that we need to talk about basic measures. What's skewness? What's kurtosis? So far we learned that the average or the median will, when you shift it, it shifts the center of the data left or right. The standard deviation will determine whether the distribution is narrow or wide. Now, one of the things that I mentioned earlier, but now we need to talk about it mathematically, is skewness. Skewness means whether the data is symmetric about the center, or it is skewed what? Positive, or it is skewed negative. Okay, so if the line tail of the data is on the right side, we say it is positive skewed. If the line tail is on the left side of the median or the mode or the average, we say it's what? Negative skew. And if it's perfectly symmetric, like the Gaussian distribution, we say that here the skewness is equal to what? It's equal to 0. So the skewness of the normal distribution or Gaussian distribution is 0. Here that number is positive, and here that number is negative. But how do we measure that mathematically? If I give you a vector, an array, a sample, and this is like the histogram of it, of course a smooth version of it, right, a distribution, then how would you give me a skewness? Well, the measure for skewness is this. You subtract each data from the average. Remember, this is what? This is the deviation. You calculate the deviation for each data point, and instead of squaring it, you cube it. Add them all together and divide it by the number of data points. In the denominator, you have what? This guy here, if you look at it, this is what? This is the variance, right? This is the summation of the square deviations divided by n minus 1. So this is what? S squared. This is the variance to the 3 over 2. If you cancel out the 3 and 2, this whole thing will be what? will be s to the 3. So it is going to be sum of the cubic deviations divided by the number of data points divided by the what? The standard deviation to the power 3. And by the way, this term here in the numerator, it has a specific name to it that we might talk about it later when we go to probabilities and stochastics. This is called the third central moment for the sample. Okay, so moments are typically summation of the data entries to any power divided by the number of data points, and the power is going to be used for the name of the moment. So if it's 3, we call it third moment. If it's 2, we call it second moment. If it's 4, we call it fourth moment. And if just the data itself, xi, is raised to that power, we just call it third moment. If the data is subtracted from the average and then raised to the power, then we call it the central moment. So central means the data is subtracted from the average, then raised to that power. Okay, so it's the third central moment divided by standard deviation cubed. That's called skewness. And you know that this standard deviation is a positive number, and the cubic power of that is also a positive number. So all really determines the sign of the skewness is this third central moment. If the data is perfectly symmetric, this moment is 0. Why? Because for any data on the left side of the average, there is a very corresponding mirror image on the right side, where this deviation and this deviation, xi minus x bar for them, one of them is negative, the other one is the exact same value but positive. And when you cube them, still, because the power is an odd number, the cube version of these two positive negative numbers, still positive negative, still equal, some of it will go to 0. In fact, for a normal distribution like this, any odd moment, any odd central moment is going to be 0, including 3. So 1, 3, 5, all of those will be 0. So skewness is 0. Now, if the data is like this, then you have the long tail on the right side. What does it mean? If you see here, I have more deviations on the right side of the average than on the left side. So I have more positive numbers raised to the power 3 than negative numbers. So some of these is not going to be 0, and some of that is going to be positive. That's why we call it positive skewness. On the other hand, when the line tail is on the left, I have more deviations on the left side of the average than on the right side. So some of these is going to be what? Negative, and that's what you can see. Okay, so that is called the skewness, and all you need is to use the command skewness in MATLAB to give you the number. So just call it with the command skewness, pass the vector to it or the sample, and you see here the skewness of this set of data is negative 0.21, which means it is going to have the line tail on the left or the higher frequencies on the right of the average. Finally, we have kurtosis. Kurtosis shows the peakedness of the data. How sharp is this peak of the data? If it's very sharp peak, we say the kurtosis is what we call leptokurtic, or we say the kurtosis here is positive. If it's quite flat and small slopes, it's not really a sharp peak, then we say the distribution is what we call platykurtic, and here the kurtosis is negative, and it's calculated such that for the normal distribution that here you see in red, it is equal to 0. How did it make it 0? Here you see there is a -3 in the formula that is added deliberately to make the kurtosis of normal distribution to 0. So normal distribution is like a gold standard. Everything is measured with respect to this guy. The skewness of it is 0, the kurtosis of it is 0, and so on and so forth. So anything deviated from that is going to have a positive or negative skewness or kurtosis. Okay, and the way that the kurtosis is measured, it is the fourth central moment, as you can see. And this guy here is clearly the variance. Of course, there is a -1 here that is missing, so it's similar to variance. It's not exactly variance, or it's the variance for the population, not really sample. So this guy in the denominator is approximately s to the 4. And this guy in the numerator, this is the fourth central moment. And again, here, -3 is subtracted from the whole thing to force the number to be 0 for normal distribution. Because if you calculate this ratio for normal distribution, it's not going to be 0, it's going to be 3. So we subtracted the 3 to make it 0. In this case, it doesn't need, I told you, for skewness, directly the numerator is going to be 0, not for this kurtosis. Okay, so if you want a very, very large kurtosis distribution, it would look like this. It's a very sharp, let me do it again, it's a very sharp peak like this. Here the kurtosis is very big positive number. And if you want something that is a very, let's say, a negative number, then you need something like this, very, very flat. And so it's a very small negative number. This is a very large negative number, I'm sorry, and this black one is a very large positive number. Okay, so the peakness of the distribution is called kurtosis. And again, all you need in MATLAB is to use the command kurtosis. Okay, so once you run it, that will give you the kurtosis of the data. Positive means it's a little bit more peaked, sharp than the normal distribution is. Okay, so these were all of the first 10 important metrics that you see in descriptive statistics. MATLAB can give you those. In Excel, you can get all of those, and each one is showing one of these 4 important properties: the frequency of the data, the spread of the data, the central tendency or location of the data, and the position within the data. And you can also use some of this data to find whether there are outliers in the data that you can exclude when you do some of these calculations. So hopefully the video was useful to you. I will see you in my next video. Thank you.